star, many times larger than our own sun,
Dalam
has a much
1,3
larger
kilometer,
exhaust child radius,
belok kiri
and
ke
it runs
Wijaya
out of
1.
fuel and can no longer keep itself hot enough. It collapses to a single infinitesimally small point known as a singularity. Its density will be infinite, and so its gravitational pull will be so strong that nothing can escape, not even light. But enough about ways black holes form. Let's jump into it. First question, what would it look like from the outside? Well, we know that gravitational fields bend space and time. Stars behind our sun will actually appear to be in slightly different locations from Earth because the sun's gravitational field bends the light coming from the stars. When it comes to the gravitational fields of larger objects like entire galaxies, or for that matter a black hole, the effect is even nuttier. Light coming from objects behind them is significantly distorted, producing smears and smudges. As seen from Earth, the blue galaxy behind this red galaxy is completely distorted like a funhouse mirror. So rather than appearing as it really should, it looks to us like a ring, a smudge all the way around the red galaxy. This is known as gravitational lensing. Now take a look at this simulation of a black hole with a galaxy millions of light years behind it. The galaxy is not really in danger of the black hole's suck, but the light coming off of that
Dalam
galaxy
300 meter,
certainly is.
belok kiri
Watch
ke
as the
Wijaya 1.
galaxy passes behind the black hole, and its light is contorted, twisted, and distorted. Now here's a really fun demonstration. What if the Earth were to orbit around a black hole? Looking from the outside, the Earth would look normal at first, but as soon as it passed behind the black hole's gravitational field would warp the light reflecting off the Earth, producing this. For the sake of simplicity, let's jump into a simple black hole, one that doesn't have a charge and isn't moving, and also isn't already sucking up a bunch of matter, so it's just there on its own. As we approach, the distortion of the sky grows greater and greater. A larger and larger portion of our field of view looking forward into the black hole will be filled with darkness. At this point, where half of our field of view has been swallowed up in darkness, we have reached the photon sphere. At this point, light is not going to necessarily get sucked into the black hole, but doesn't necessarily leave it either. Instead, at this magical point in space, light, photons, can actually orbit the black hole. If you were to stop here for a moment and look to the side, you could theoretically see the back of your own head, because light reflecting off the back of your head would travel all the way around the sphere of the black hole right back to your face. A gravitational field not only warps space, it also warps time. Now, for most intents and purposes here on Earth, we never have to worry about that. But near a black hole, gravity would be so strong that an observer standing watching you jump into the hole would see something quite strange. They wouldn't see you get sucked quickly into the hole. Instead, they would see your approach become slower and slower and slower until you reached a point known as the event horizon. This is a point in space where, once crossed, there's no going back. It is at that point that light can no longer escape. And so to a person watching you fall into the hole, that would be where
Dalam 300 meter,
you would seem
ambil
almost
lajur
frozen
kiri.
in space, the light coming off your body becoming increasingly red-shifted until you simply faded into nothingness. They would never see you cross the event horizon. But for you, of course, everything would seem fine and dandy. You would continue past that horizon to your now inevitable death. As you continue to approach the black hole's singularity, your view of the entire universe would get compressed into a smaller and smaller point in space behind you. If the black hole we're jumping into is larger,
ambil lajur
things
kiri ke
might actually
Wijaya
be
1.
quite comfortable at that event horizon. We'll know that we're never going to escape and that our lives are pretty much over, but it
Dalam
might take us
400 meter,
hours to
belok
actually
kiri
reach a
ke
point where things
Prapancaraya.
might hurt. Why would they hurt? Well, the closer you get to the singularity, the more significant the difference in gravitational pull is across space. And so parts of me that are closer to the singularity would be pulled more strongly than parts that were facing away. And my entire body would be stretched toward the singularity. The effect would be so incredible, scientists don't usually call it stretching, they call it spaghettification. Once you reach this point, you would be dead. few molecules would be violently ripped and stretched apart, and when they got to the singularity, well, we don't really know what would happen. Perhaps they would completely disappear in violation of all the laws of physics, or maybe they would reappear elsewhere in the universe. It's believed that a moving or spinning black hole might actually create what is known as a wormhole, a way of transitioning across space faster than light. Not in any way that violates the laws of science, but in a way that takes advantage of the universe's dimensions. For instance, if I wanted to get from this point to this point, I'd have to travel the distance. But theoretically, a wormhole would do something really crazy. For instance, this. Now, the 2 points are right next to each other, and I can travel between them almost instantaneously. But again, this is all theoretical. Luckily, we do have a possible way of analyzing black holes right here on Earth. Enter the dumb hole. Just as a black hole does not have light to escape, a dumb hole is an instant black hole. It won't allow sound to escape. It doesn't have to be nearly as powerful, and scientists have been able to create dumb holes in laboratories using special fluids traveling at the speed of sound. A lot of progress still needs to be made in the world of acoustic black holes, but we may be able to learn an amazing amount of information about how black holes work by looking at how sound is treated in a dumb hole. Now here's another good question. What would it look like to travel at the speed of light, say, toward the sun? Well, surprisingly, you wouldn't just see the sun immediately rush up toward you. No. In fact, initially, it would look almost as if the sun were receding away from you. Why? Because your field of view would vastly increase in size. You would be able to see stuff almost behind you, and here's why. As you sit there, not moving yet, looking at the sun, there's light coming from stuff behind you. But if you travel the speed of light, you will actually reach that light coming from things behind you. As you reach light speed, your field of view would expand like this, concentrating on stuff behind you. But where are you in the universe? Well, here's a better question. Where is the center of the universe? This might sound crazy, but it's everywhere. This is known as the cosmological principle. No matter where you are in the universe, everything else will seem to be moving away from you, expanding in the same way. The universe is expanding, but not like a balloon getting bigger and all the people inside it. Instead, it's as if we are the surface of the balloon. If you were to put a bunch of dots on a balloon and blow it, all of the dots would move away from each other at the same rate, and on the surface of the balloon, there is no center. Take a look at these two balloons. They are exactly similar, except the top layer represents a line of expansion at the bottom. Let's say that you build these dots, and you can measure where everything is moving away from you. There's much more difference between the top and the bottom and the cross. As you do this, it looks like the center of the expansion. I can do this with a dot. As soon as I choose a dot, you can find a reference and immediately becomes the center of the expansion. So while dying in a black hole would be lonely and scary and morbid, when you look up in the sky, think instead about this. No matter where you are, or who you are, or what your friends or your parents tell you, you really scientifically are the center of the universe. Finally, what if our universe was a Googleplex course of price? It is nowhere near that large, but if it was, it would be so voluminous that statistically, it would be nearly impossible for there not to be an exact copy of you somewhere else out there in the universe. To see why, I highly suggest that you click right there and check out Brady Hammond's new channel, Number Fire. It's part of the YouTube original channels, and I've worked with these guys before. They're amazing. They're my favorite kind of geeks. So, check out that video, watch their other stuff, and if you like math, I highly suggest that you subscribe. And as always, thanks for watching. Michael here, and I am in Regent's Park in London, joined by Tom from /Tom. Awesome channel, check it out. This camera belongs to Tom, and Hazel is operating it right now. Yeah, that's her giving a thumbs up, which I'm sure just looked like a blur, but the point is, we're going to do information today it's also the United Kingdom, which is in Europe. Okay, and we've also got another term, Great Britain. Well, let's unpack all these terms and today learn about geography.
I may have failed geography.
Can I find someone else? Now, if we're going to talk about geography, I think we should go all the way back to a time when there was no geography. That's right. Way before YouTube existed, our solar system was nothing but a mist of dust and gases, what is known as a solar nebula. But then, about 4.6 billion years ago, something majestic happened. We don't know exactly what caused it, but some scientists believe that the shockwave of a nearby supernova hit our nebula, causing it to start spinning and contracting. Now, as things collected together, their overall gravity got stronger, and they pulled more stuff in it, and boom, we've got a sun. A 500 million years later, and the disk of junk circling around the sun starts coming together in its own way into what we now call the planets. One of these planets I've actually visited, and it's called Earth. But before we get ahead of ourselves, what the heck is the moon doing there? I mean, here's the problem. When you look at all the terrestrial planets, all the planets near us, near the sun, they all have very similar structure, and they all have the same big metal core, and they all have very similar densities. But the moon is very not dense, and it doesn't have a similar structure. It doesn't have a huge, dense metal core. In fact, when we visited and brought back dust and rocks to analyze what the moon was made out of, we found that the moon was made out of the same stuff that you find in Earth's crust and mantle, but not Earth's core. This discovery gave rise to a pretty awesome idea that the moon is actually made out of what used to be Earth. About 4.5 billion years ago, there used to be another planet called Theia. It was a little bit smaller than Mars, but it had an unfortunate orbit. It was fine for millions of years, but eventually, and what did happen to it was that it collided with Earth. Now, it's believed that the collision happened quite slowly, and the centers, the cores of both Theia and Earth fused into one. And material from the mantle and crust of Earth wasn't just scattered, but it was forcefully ejected, literally launched into outer space. It circled around Earth, and scientists believe that it took only about a week for all that Earth material out in space to coalesce into what we now call the moon. Oh, and by the way, if that's how the moon formed, it was such a strong collision, the actual axis that the Earth spun on was tilted 23.5 degrees, which to this day is why we have seasons. Wow. Alright, so 4 billion years ago, the continents as we know them began to emerge. You know, these pieces of the Earth's crust that have cooled down, that are floating around on Earth's molten liquid insides. Now, they move, and they've been in constant motion since they began, but they move very, very slowly. Every 300 to 500 million years, the continents all converge into what's called one big supercontinent. All the land in the entire Earth all together, and the rest of it covered in ocean. The most recent supercontinent is kind of famous. It's called Pangaea. But scientists believe that there may have been 4, 5, 6, or even more supercontinents that existed before Pangaea. What's really mind-blowing is the fact that eventually there's going to be another Pangaea, another supercontinent. And based on calculations, the Earth at that time will look like this. But like I said, these land masses are moving very, very slowly. And so, for that reason, it is worth learning their names as they are now. Which brings us back to the question of England, United Kingdom, Great Britain, British Isles, and what all these terms mean. Let's begin zoomed out. The British Isles and Ireland are a collection of 6,000 islands off the coast of Europe. The term Great Britain refers to the largest of these islands. Now, Great Britain contains 3 separate countries, England, Wales, and Scotland. If we add Northern Ireland into the mix, we're now looking at what is known as the United Kingdom, or the UK. The Republic of Ireland is a separate country that is not part of the United Kingdom. And by the way, England is where London is, which is where Somewhere in the City was. Which brings us back to Regent's Park. And, as always, thanks for...
Could you guys stand still for a second?
Is that good enough for you?
Blurry.
To learn more about Great Britain, Ireland, overseas territories, and even Canada, you really must check out CGP Gray's explanation video if you haven't seen it already. This guy is incredible. You can also check out the channels belonging to people who helped me with the intro and outro for this video. We've got Tom and Dude, Where's My Challenge? Hey, Vsauce, Michael here. What if every single person on Earth jumped at the exact same time? Could it cause an earthquake, or would we not even be able to tell? Well, first things first, let's talk about the Earth's rotation. The Earth spins, it's why we have night and day, and it spins quickly. At the equator, the Earth is spinning at more than 1,000 miles per hour. Now, a spinning ice skater can speed up by moving mass closer to the center, and the Earth is no different. In fact, if you get down on the ground right now and move your mass closer to Earth's center, technically you will speed up Earth's rotation, making this day shorter.
Dalam 1 kilometer,
The change
keluar
that would
ke
make
kiri
Earth's
ke Krukut
rotation
Raya.
is way smaller than we can even measure, but it is calculatable, and the impact can be quite impressive when you talk about redistributing more mass than just one person. For instance, last year, the earthquake in Japan redistributed so much of Earth's mass towards the center that every day since then has been 1.8 microseconds shorter. But that was a giant geological event